support community resilience.
All right, thank you so much. So clearly I have the enviable, or maybe not so enviable task of discussing sea level rise at a conference in Idaho. There is going to be some nerdy stuff about sea level rise in here, but really the takeaway is that this is about how we communicate risk. Efforts that we've made to improve how we communicate risk, in this case associated with sea level rise and climate change impact, to communities that we work with on the North Olympic Peninsula. I want to take a couple minutes to just acknowledge my co-authors on this talk. There's a bunch of them in there: Sasha Peterson, Matt Fugere, Cindy Jane, Jake Bell, and Kate Dean, who were partners on this project focused on the North Olympic Peninsula. Cindy and Sasha are here in the room. And then Bob Kopp, Eric Grossman, Guillaume Mauger, and Abbas Hushmand are all sort of sea level nerds that I work with and benefited from discussions with, or in some cases they contributed directly to this project and this talk. Both Eric Grossman and Guillaume are here at the conference. Okay, so the focus, I'm going to start sort of with the end at the beginning. So the overview and the message is that for this project that we're just wrapping up, focused on the North Olympic Peninsula in Washington State, we've come up with an approach and tools for projecting sea level rise at the community scale. And there was a few innovations in this project that we think really helped with communicating the risks associated with sea level rise to the communities that we worked with. And the ones that I'm going to focus on are: we present the projections in what we call a probabilistic framework. Hopefully this will become clear what that means in a few slides. And then we took into account these really sort of very, very granular local variations in vertical land movement in particular, which occur at the community scale on the North Olympic Peninsula in Washington State. And then we also made an effort to rigorously incorporate sort of the storm surge component, the flood component, this kind of interannual variability component to water level that sometimes is hard to sort of account for or think about when you're also trying to think about sea level rise or average sea level. By the way, again, the project is just wrapping up, and some of the final products, maps, reports, everything is available online. There's a long, awful link there, but you can also go to noprcd.org, and then it links right from there as well. And so just a tiny bit of background about this project. I won't go into detail about the project in general, but it was essentially a community-based assessment and adaptation planning process focused on the North Olympic Peninsula in Washington State, led by the North Olympic Conservation District and then supported by Sea Grant, who I work for, and then Adaptation International. There's going to be a talk that explores the project in more detail tomorrow at 11:10, so make sure you catch that, by Cindy Jane, Planning for Climate Change Across a Rural Two-County Geography. It was a pretty inspiring project in its entirety because of the diverse geography and the diverse populations that were sort of involved. The geography itself is shown in this map. This is the North Olympic Peninsula in northwest Washington State. I think I have a laser beam. Does anyone know how to work? There we go. And so just to orient you, this would be British Columbia. This is Victoria, British Columbia up here, and then Seattle would be down sort of right around here, and Puget Sound just off the map. And I should also point out something obvious, that this project had a focus, in some ways, an emphasis on sea level rise, because the communities, the major sort of areas of development in the project area, are all coastal communities. So sea level rise is a significant impact, obviously, for those communities. Okay, so our starting point in terms of thinking about sea level rise and how we wanted to communicate it, we had sort of started with two fundamental observations. The first is that sea level projections contain more complex uncertainty than is typically represented. And so what we're accustomed to seeing is, maybe a single curve that might represent sort of a median projection, maybe from a variety of model runs. If we're lucky, we get some rigorous assessment of uncertainty, something like a standard deviation sort of accounted for somehow. Usually you get sort of some kind of high-low range, some kind of vague statement about high-low ranges. Obviously the uncertainties are far more complex, and so we wanted to try to account for that as best we could. The other observation is that assessing exposure to sea level rise is complicated at the community scale by interannual variability. So what we mean there is this is monthly sea level. This is from Seattle, Washington. And this is from Nia Bay over the entirety of their records. And there's a bunch of up and down wiggle there, right? So how do we account for that? How do we communicate that to communities? How do we sort of help them understand that in relationship to the change in sort of the mean sea level? And then the other is that we have these local factors in our area primarily driven by differences in vertical land movement, what the land is doing. That's also represented here where you have sea level in Seattle rising, relative sea level, and then relative sea level in Nia Bay falling, and that's because of differences. And these communities, by the way, are relatively close to each other. They're within about maybe 100 kilometers or 100 miles as the crow flies. And so these are significant differences in vertical land movement between those communities and has implications for what they would expect for sea level rise. So then our goal in approaching this project was to better communicate their exposure at the community scale, accounting for as many future hazards as possible, and then using locally relevant and credible data. And then we wanted to do it all for pretty cheap. And I want to sort of shout out 2 years ago, I was at this conference and I saw a talk by Katie Seraphin, who's a grad student working with Peter Ruggiero at OSU. She presented on some of the work that they do in that group, which is phenomenal, trying to sort of account for all the different processes that influence coasts, and they sort of present it all probabilistically. It's beautiful work, but at the end of her talk, I sort of asked, how do we do what you do in an academic setting in an operational setting where we might have a few weeks to do this rather than, your PhD term. So this project is essentially an attempt to do that, but on a sort of a cheaper scale within a sort of the project context. So our first step, I want to present 4 steps, kind of how we went about doing this. Our first step was to utilize these fully probabilistic oostatic projections. So this is kind of a new way of presenting sea level rise that makes an attempt to rigorously account for the various uncertainties in the contributing factors to sea level rise. Every component, whether it be the rise in sea level due to warming of water, for example, and the expansion of water, or whether it has to do with the melting of Antarctica, all of those different contributions have uncertainty associated with them. So we turn to this work by Bob Kopp, again from Rutgers, published in 2014, published a paper in which they attempted to account for all of those uncertainties and present global and regional sea level projections with their full probabilities displayed. And so, sort of what you're seeing here is a series of curves, and then each of those has a probability of occurrence associated with it. Here I show 2 different emission scenarios. And you can see there's a huge range, right, in sort of the projected sea level rise, some very low ranges, some very high ranges. And what we really liked about this is that we saw that it was a way that we could provide communities with more nuanced information that they could use to make more elaborate risk-benefit decisions about whether it be a particular piece of infrastructure or a particular planning decision, something that might have high value. You might want to plan for something that was occurring at sort of a lower probability of occurrence, but since it was a high value piece of infrastructure, you want to take that into account. So we really liked immediately what was provided here, and we actually this was published when we were midstream in our project, and we immediately pivoted to be able to use these. It's also worth noting that part of the contribution that Bob Kopp made was not only providing the paper, but providing a set of tools, MATLAB-based tools that you could use to go in and access this information at a very granular level, at a regional level. So these are actually projections for our study area, the Strait of Juan de Fuca in particular. So really, really nice contribution in my view. The next step is that we had to take into account these variations at the community scale and vertical land movement, because we wanted to provide the communities with a projection of relative sea level. What's going to happen in their community. And as I sort of mentioned, this is the North Olympic Peninsula in Washington State. There's a lot of variation in vertical land movement driven by tectonics. We live in a tectonically active region, so the land is doing funny things as a result of that. So we actually did our own analysis to come up with our own estimates of coastal vertical land movement at the community scale. We did it by coupling data from tide gauges with data from continuous GPS stations. And both are shown here. The black squares are tide gauges, and these round circles are GPS stations. And this curve at top basically shows you our estimate of vertical land movement. This is uplift, this is subsidence across this transect. Again, the squares are the coastal estimates at the tide gauges, and then these circles relate to the GPS stations. And so you can see there's a gradient. Nia Bay is uplifting quite rapidly, but once you sort of head east into the eastern part of our study area, we see a pattern of subsidence. So that's going to have significant implications for projections for those communities. It's worth noting that the reason that we did this is because some of the previous assessments that communities had been using had really generalized land movement across a pretty large area. And what we saw as a result of that was communities sometimes being paralyzed by indecision and sometimes being really confused about what their sort of future might look like. And in some cases, we heard things like, we don't have to worry about sea level rise because we're uplifting so rapidly and things like that. So we really wanted to be really granular about this to provide the best information to communities to promote adaptation. And then finally, we also wanted to account, again, for that interannual variability. It's not just about sea level rise, it's about how sea level rise couples with other factors that drive elevated water levels. Storms, for example, storm surges, El Nino years when you have elevated water level. So this is a very complex problem. Our particular approach was, again, to turn to the tide gauges and pull information from the tide gauges about the highest water levels occurring in every year. So what you see here is that information for Nia Bay presented as a histogram. So you got number of years over here. It's an 80-year record, and then you've got essentially the highest water level occurrence represented as meters above mean high water, just a tidal datum that we used as our project datum, and then a curve fit to us. And what we could then do is we could pull a probability from this curve. We could say, what's the chance that you'll have a storm event of this height versus this one? And so once we had those represented as a probability, they could be combined rigorously and statistically with the probabilities associated with sea level rise. So I think of this as kind of like the Hurricane Sandy lesson. We have to be able to represent not only sea level rise, but sort of the chances of occurrence of sort of an extreme event, essentially, to a community, and allow them to think about what that means for their community. And then finally, the fourth part that I want to emphasize is one of the things that we struggled with. Again, we didn't have much time, so we didn't struggle with it that much. But we did have a lot of discussion about how do we map this kind of information. There wasn't really too many templates that we could turn to about how do you map this kind of probabilistic information, which is pretty rich in detail. And so the approach that we took, this particular example is for an area that we mapped at the end. This is the Dungeness River Delta, for those of you that are familiar with the area, one of our sort of most low-lying kind of landscapes in our project area. So what we chose to do is we mapped relative to mean high water. We thought that was sort of a relevant datum. It's kind of the top of the beach. Anything above that potentially represents problems. We mapped for 3 time steps. And we really emphasized sort of these near-term time steps because, again, the focus here was on planning. And what we were hearing was that planners wanted information about more near-term. 2100 was a little less relevant. We created 2 map sets. We created a map set for sea level rise and then one for that annual extreme still water level. That's what SWL is here. So the annual extreme water level. So we ended up with a total of 7 maps per site that we mapped. We used pretty good LiDAR data available to us with accuracies of probably around 15 centimeters. And then we only mapped the upper 50% of the distribution. So here, the dark blue is the 50% probability of occurrence. Then we go to 25, 5, and 1%. And the reason we didn't map some of the lower parts of the distribution was because you tend not to see them on these maps. They tend to be sort of represent kind of the lower ranges of sea level change, and so you tend not to be able to resolve them on a map at this scale. So limitations, there's a variety of them. There's definitely places that we would like to go to, and that I think, if we can figure out ways to do it in kind of the operational context, then we can provide a lot better information to community. One is in regards to waves. We have nothing in our project that represents impacts due to waves, but certainly waves are an impact, even in the inland waters of Puget Sound, for example. These two photos are from Alki Point in Seattle. This one was shot during the sort of co-record high water level in 2012 in Seattle. You can see it's a still water event. This one was shot last year when the water level as measured by the tide gauge was almost 2 feet lower, but obviously had the waves thrown on top of that. So the flooding was identical effectively. So waves are important. We have to represent them, but currently we have no information that we can use to do so. The second one is that we just, like a lot of sea level rise assessments, we just draped our sea level over the existing landscape. Where we need to head is we need to head towards being able to project how the landscape will respond to that. There are efforts to do that. This is an example from Heather Behrens, who was a graduate student of Peter Ruggiero's in Oregon. She did some work on the coast of Oregon trying to project coastal erosion with sea level rise scenarios. Really nice work, but it's very, very data reliant. Most places don't have the kind of data they have access to in coastal Oregon. We're making efforts to collect that for Washington State. This is an example from Eddy's Hook outside Port Angeles, just collecting shoreline change data over time. We also, of course, have continued questions about how accurate our vertical land movement information is. It's a hard thing to measure, but it's important to communities for resolving sea level rise impacts. And then, of course, how we communicate probabilities is an area that we'd really love to sort of improve on over time, and I think that we will. It's definitely where things are heading. So despite those limitations, the perceived response, I think, was good. We didn't rigorously assess how our project team responded to sort of the way we presented sea level rise information. But our my general impression was that it increased their understanding in terms of the sea level rise impacts in our study area. And this, what we saw was when we moved into the vulnerability assessment adaptation strategy development process, sea level rise was definitely there, definitely part of the discussion. The project team seemed to embrace and understand what we were presenting and trying to communicate. So that was at least a good start in terms of understanding how this was used in the way that we wanted it to be used. So I'm going to end there. Thank you so much. And I don't know if I didn't get the stop sign, so I think there's time for, or did I?
Yeah, you've got a minute.
Okay, great. I have a minute. Thank you. Can I just go for it? Yeah. Okay.
I was wondering if you tried putting in the probability of earthquake and
No. Yeah. Right, exactly. Great point. We did not, but every time I presented it, except for this time, I usually mention that because the vertical land movement we think is almost entirely tectonically driven. Those patterns are based on sort of us continuing not to have a major subduction zone earthquake event. If it did happen, then those patterns would change. It would be awesome to be able to incorporate that or do some kind of dual hazard assessment, coupling tsunamis with sea level rise. We're not quite there yet. Yeah.
What about including some geomorphic element to it, like for that hazard risk?
Well,
If you have an earthquake, you had tsunami, and then you overlay the geomorphic issue, like what types of soil or like underlying conditions you have under there.
yeah, so again, I think that would be something that we would do as part of like a multiple hazard assessment, and we're trying to go there, or at least I'm trying to go there. I know others are as well, but we didn't incorporate it here.
If you're going up and then you have an event that triggers a tsunami, but you're on soil that's going to just go.
Yeah, and more to the point, like communities like Nia Bay that are currently uplifting fairly rapidly, they're expected to subside very rapidly during an event. So there'll be a variety of interesting complications. Yeah. Oh, sorry. I'm done? Okay, sorry. I'm here, happy to talk.
Thanks, Ian.